Okay, quick review video for you for the test tomorrow, Wednesday. The study guide, of course, has been up on Schoology for a good while here, so feel free to take a look there. That's what you should know. Our Nobel Prize article, which is on Schoology, to be able to summarize what the research was that won the Nobel Prize and how it affects your life. Sounds like a nice short answer question. Periodicity and periodic law. Periodicity is the fact that something repeats over time. It's regular repeating pattern. And that's one of the ways that the periodic table is organized. Mr. Mendeleev organized his based on atomic mass and periodicity. But the modern periodic table is organized by atomic number. So again, if you look here at the periodic table, it is ordered in number. But again, there's these skips, there's these breaks, there's these movements. And why did we, when we got to 10, why did we go to 11 over here instead of just making another one going this way? That's because of periodicity, the fact that these groups have this regular repeating pattern of properties. The parts of the table, metals, nonmetals, metalloids. Obviously, the blues are the metals, the greens are the metalloids, the yellows are the nonmetals. Metalloids kind of have properties of both metals and nonmetals. Metals have properties like they are solid at room temperature other than mercury. They are very pliable, very malleable, bendable, they're shiny. They tend to have high melting points. They conduct electricity and heat very well. The nonmetals are exactly the opposite. Many of them are gas at room temperature or even a liquid like bromine. They don't conduct electricity well or heat well. They are brittle. They don't like to be bendable and malleable. And the metalloids are somewhere in the middle. So that is their names. You should certainly know groups. The main groups, transitions, inner transitions. So main group are groups 1 and 2, 13 to 18. And 3, so that's main group, 1 to 2, 13 to 18. The inner transitions are 3 to 12, and then, boy, I'm sorry, must be early. The transition elements are 3 to 12. Sorry, I had to sneeze. And then the inner transitions are these guys down here. You should be able to identify the periods and the groups. So the periods are the horizontal and the groups are the vertical. You should be able to identify the names of these different things, alkali metals and alkaline earth. Notice how similar they are to each other. The alkali are these and the alkaline earth are group 2. Group 17 are the halogens and group 18 are the noble gases. 17 and 1, they like to get together because this is a +1 and this is a -1 as far as their charges go. These guys give away one of their electrons, their valence electron, and these guys take that one. We'll talk more about electrons in a moment here. In our element card lab, we used the main way that we organize the element cards. We're using atomic mass and periodicity, because on those cards we didn't have atomic number. So you ran across some of the same problems that Mr. Mendeleev had, that there were some elements that seemed like they should go in certain places and it didn't quite work. If I zoom in here, you can see that iodine and tellurium, these were two that you all were struggling with. Iodine seems like it should be here based upon its atomic mass. And Mendeleev said, oh no, iodine's mass must be wrong. Well, no, it wasn't wrong. He just didn't know about atomic number. He grouped iodine here because chlorine, bromine, iodine, these are what we call one of Dobriner's triads, if you remember reading in the textbook about this. These were groups of 3 that we knew had very similar properties, chlorine, bromine, iodine. So he knew they had to go together in the same group, but to put them in that order messes up their atomic mass. So here are the trends that you should be comfortable with. That atomic radius, how big the atom is, decreases from left to right and increases top to bottom. Ionic radius you don't have to worry about. We didn't spend much time talking about that. But the point is that for positive ions, the higher the positive is, the smaller it gets. So a +3 is smaller than a +1. For the negative ions, the size increases as the charge increases. So my -3s are larger than my -1s. Electronegativity, how attractive the atoms are to electrons, that increases from left to right and decreases top to bottom. And ionization energy, that increases left to right and decreases top to bottom. And again, how I would do that would be to give you an element and say, which has a higher electronegativity, lithium or fluorine? And of course, you know it increases as I go to the right, so fluorine would be the answer. Same thing, lithium or francium, you know that it decreases top to bottom, so therefore lithium would have the higher. If we continue on down the list here, the gaps in Mr. Mendelev's periodic table, that was where he thought, hey, there has to be an element here that we haven't found, but it fits in that spot. Germanium is an example of that. That we had gallium, we had arsenic, we actually had silicon and tin at that point, and there was a spot that he said, there has to be something that goes right there. And sure enough, germanium was found. He predicted the properties of it, and he was nearly right on, which made scientists really believe, hey, no, this is correct, what this guy is talking about here. Our alkaline earth elements lab, our reactivity, group 2 and 3, right? As you move down, it gets more reactive. As I move to the right, they get less active, just like in the demonstration that we did with the group 1 elements in class. And aluminum did not react in our testing because, maybe I should leave you hanging with this one since we're doing the lab today, but it didn't react because it is not as reactive as the other ones. It did not meet the criteria to react with the pieces that we had. Demonstration of group 1, we talked about those, and again, we did not demonstrate potassium because it is very reactive in the water, and we didn't want to blow the school up as much as you all might have enjoyed that. Our principal energy levels, how many electrons do each principal energy level hold? Well, let me pause for a moment here. All right, I wanted to get to this diagram here. We're talking about energy levels, and you can see that in energy level 1, that holds 2 electrons. In energy level 2, that holds 8. Energy level 3, that holds 18. Energy level 4, 32. We've also broken it down into its sublevels, that the S's hold 2, the P's hold 6, the D holds 10, the F's hold 14. And that shows you how they fill up. 1s2, 2s2, 2p6, 3s2. So can you guess what element that would be? The 3s2 ending would be magnesium. So that would be the electron configuration for magnesium. Again, Heisenberg's uncertainty principle says we can't know both position and the velocity of an electron at the same time. So we need to make sure that we can say the electrons are in certain places or not. Atom sublevels, SPDF, I already talked about all of these pieces. That Aufbau principle means that the electrons will fill up the levels in the order of the least amount of energy. So going back to that little diagram there, my 1s will fill up first, then 2s, then 2p, then 3s, and we would think maybe that it would just keep going like that, right? We would think that the energy levels are these separate pieces, but in actuality they aren't. They're all intertwined together, so that the 4s actually fills before the 3d does. And how do you know that? Well, you can either memorize this Aufbau diagram like this, or you can just simply follow that periodic table. The periodic table shows here is the order they fill up, starting with hydrogen, moving to the right, following the atomic number. Electron configurations, you should be comfortable with that longhand or shorthand configurations. And why do the sublevels fill up in the order they do? It's simply, it takes the least amount of energy possible. The least amount of energy. So it takes less energy to put something in the 5s than it does to put it into the 4d. It takes less energy to put it in the 6s, all the way up in energy level 6, than it does in the 4f. It's further away from the nucleus, so it takes more energy to keep it in that sublevel. As I roll down, don't forget about those two exceptions, chromium and copper. that when you look at the PT, you would think that chromium is 4s2 3d4, but in actuality it's 4s1 3d5. The extra electron from calcium that would have gone into 4s instead goes into the 3d. Same thing for copper. It looks like it should be 4s2 3d9, but in actuality that calcium electron goes and becomes 3d10. There are lots of other exceptions, especially down here in the inner transition elements where lanthanum and actinium kind of bounce back and forth, but all you need to know are chromium and copper as the exceptions. The periodic table controversy article, the conflict discussed is where we should put lanthanum and actinium, whether they should stay here in group 3 or they should come down and be the first ones of this F sublevel. What reasons are given to defend the placement of putting them there is because they have properties that match scandium and yttrium, so it's better to put them in that same group, and also that they're one extra electron. So 6s2, is this a 5d1 or is a 4f1? Well, actually, we found it is a 5d, so it just makes sense to put them there in 5d. Why does our textbook and the author place there? Again, because it just makes more sense. It's certainly easier for us to do our electron configurations, that we know that there are only 14 in this F sublevel. If you count these squares, there are 14 there. And we also know that these guys have that electron in the 5d and 6d, so therefore it makes more sense to keep it there. And last but not least, you should be able to use that periodic table and the electron configuration to determine the number of valence electrons for each of the main group elements. So we know for the main group elements that those in groups 1 and 2 have 1 valence electron, 2 valence electrons. These guys have 13, excuse me, not 13, you have to subtract the 1. So 3 valence electrons, 4 valence electrons, 5, 6, 7, 8. And of course the charges, this would be a +1, a +2, a +3, because they give away their electrons. This would be a -1, a -2, and a -3 for these non-metal pieces. In group 14, we were kind of messed up because we've got a non-metal, 2 metalloids, and 2 metals. So these guys sometimes will give away 4, sometimes will give away 2. It just depends. Excuse me, group 15 usually will be a -3 for these guys, but can be even a +5 or a +3. It just depends. Bismuth is a goofy one. We'll talk more about that coming up. Hopefully that's helpful for you. Going through our review, you will do well.